In previous modules, we looked at the basic concepts of the theory of constraints. Every organization has a goal. We measure our progress towards the goal using throughput, investment, and operating expense. And the thing that prevents us from achieving more of our goal is the constraint. In this module, we will learn how to improve performance using TOC's 5 focusing steps. So how do we improve the performance of our organization? In 1984, Dr. Goldratt published his breakthrough business novel, The Goal. It was an instant classic, and in the bestseller charts for years, winning critical acclaim and plaudits from readers. It's been translated into over 35 different languages and is estimated to have sold more than 7 million copies. Many of the biggest and best-known business schools have it on their recommended reading lists. And it's required reading for executives at many companies, including Amazon. Written as a novel, The Goal tells the story of Alex Rogo and his management team who run a manufacturing plant in the United States. As Alex arrives at work one morning, he finds his parking space occupied by his boss's car. In a meeting a short while later, Alex's boss tells him that he is not happy with the plant's performance. He tells Alex that if it doesn't improve within 3 months, the plant will be shut down, leading to the loss of over 600 jobs. Alex is devastated by the threat and has no idea what he can do to avoid this nightmare. A week or two later, Alex is traveling for work and happens to bump into his old physics professor, Jonah, and their conversation changes his life. Over a coffee at the airport, Jonah explains that he is currently researching productivity and efficiency in manufacturing systems. This starts a conversation that causes Alex to question everything he thought he ever knew about manufacturing. Frustratingly, Jonah refuses to answer Alex's questions, but the questions Jonah asks Alex cause Alex to reevaluate his assumptions about how his plant really works. The book goes on to tell the story of how Alex works with his leadership team to transform the performance of the plant and avoid the devastating prospect of it being closed down. He even ends up with a promotion. While Jonah doesn't spell it out, what he explains to Alex is TOC's 5 focusing steps. The 5 focusing steps gives us a step-by-step process to improve the performance of any system, directing our attention to the one thing that really holds us back, the system's constraint. The first step of the focusing steps is to identify the system's constraint. As we know, TOC argues that the constraint is the one thing that holds us back from achieving more of our goal. So, if we want to improve the system's performance, we must first identify the constraint. Step 2 is to exploit the system's constraint. A minute lost at the constraint is a minute lost for the whole system. It is absolutely critical that we squeeze everything we possibly can from the scarce capacity of our constraint. Step 3 is to subordinate everything else to the constraint. Our ability to effectively exploit the constraint usually relies on non-constraint resources subordinating themselves to decisions we make to exploit. Step 4 is to elevate the constraint. After several iterations through steps 1, 2, and 3, we may find further performance improvement is impossible without adding more capacity at the constraint. Step 5 is to go back to step 1. Do not allow inertia to become the constraint. If you continually strengthen the weakest link, at some point it will no longer be the weakest. So in step 5, Goldratt warns us not to become set in our ways and assume that things will continue to improve if we keep on doing the same thing. He highlights the danger of not regularly reassessing how our system is working and what constrains us from achieving more of our goal. We must reassess after we have improved the constraint's performance to ensure that our focus continues to be on the right area of the system before we embark on another round of improvements. Let's now look at each of the steps in a little more detail by running through some simple scenarios. Imagine a simple process like in the diagram. Work in progress flows from left to right, passing through each work center in turn, from A to B, B to C, C to D, D to E, and finally E to F. The height of the blue bar at each work center indicates the level of capacity available at each step of the process. Step 1 requires us to identify the constraint if we want to improve performance. Looking at the diagram, where is the constraint in this process? Remember, a constraint can be something that governs the throughput of the system, like a machine or market demand. Or it might be something that governs the behavior of the system, like a regulation or policy. Based on capacity alone, you might argue that it is work center D, as this has the least capacity of the 6 work centers. However, without knowing the level of market demand, it is impossible to say for sure. Notice the 2 lines that are now on the diagram, labeled X and Y. If market demand is at the level indicated by the line labeled X, then we would have an internal constraint at work center D. This is because market demand is higher than D's capacity. Therefore, we have an internal capacity constraint limiting our throughput. If market demand was at the level shown by line Y, we would have a market constraint. This is because market demand is less than the capacity we have available to us throughout our process. In this scenario, even Work Center D has more capacity than market demand and can comfortably keep up. Let's assume that market demand is at the level indicated by line X. In this scenario, Work Center D is the constraint. It is the one part of the process that cannot keep up with market demand. What else should we expect to see in this scenario? In this situation, we would expect to see large queues of work in progress upstream from Work Center D. Why is this the case? In most organizations, orders are taken from the market and released to manufacturing without reference to the available capacity of the constraint. This means more work in progress is entering the system than the constraint can cope with, resulting in queues upstream. The biggest queue will be located in front of the constraint, as Work Center D has the least capacity. We should also expect to see big queues further upstream in the process as work in progress backs up towards material release. Downstream of the constraint, the opposite is true. Work centers E and F have more capacity than D, and are able to quickly process any work that D completes, so the queues of work in progress downstream will be relatively small. This simple analysis holds true in numerous different environments when using the 5 focusing steps. Now let's look in more detail at step 2. Exploiting the system's constraint means to squeeze the most from the little that we have. Every minute on the constraint is precious, as it determines the output of the overall system. Let's assume that Work Center D is a machine in a manufacturing plant. Exploit in this instance means eliminating any unnecessary downtime on D. While many plant managers pride themselves on their plant's efficiency, it is often the case that the constraint loses time, and for numerous different reasons. For example, if the constraint runs out of work, it will inevitably stop, wasting precious time. To exploit, the obvious answer is to keep a buffer of work in front of it, so that it always has something to work on. This is a simple first step to increasing throughput and achieving more of our goal. Time may be lost at shift changes, when work is stopped for operator handovers, or at break times, when the operator is not present. If we stagger shift changes and arrange cover for breaks, we can avoid more lost time. These may seem like small changes, but they soon add up to significant amounts of capacity uncovered and additional throughput gained. There are numerous other ways in which time can be lost. It is always instructive to spend time observing the constraint, as you will frequently get good ideas on how to prevent lost time. To properly exploit, we must rigorously identify each cause of lost time and methodically eliminate all of them. Frequently, the increases in throughput from this process are huge. Let's return now to our thought experiment. D is the constraint of our process. If we could generate more throughput, the market will accept what we produce, and we would move closer to our goal. What then should we expect to happen if we were to improve the performance of Work Center D? Firstly, we would increase the productive capacity available at D. The blue bar representing D's capacity would increase, reflecting D's ability to do more work within the period. But what else would we expect to see in the plant? If D's productive capacity increased, inevitably the level of queuing upstream from D would start to fall. This is good news, as throughput would have increased, and the lead time for work in progress to get through the plant would have already decreased. What happens if we identify the wrong work center as the constraint and improve a non-constraint instead? Let's assume that the location of our constraint is unclear, which can sometimes be the case in a busy manufacturing plant. So, as we need to improve performance, we decide to focus our improvement efforts on our best guess, which is Work Center C. What would we expect to see in that case? If we increased the productive capacity of C, queuing upstream from C would go down, but the queue in front of Work Center D would go up. This would quickly show us the location of the real constraint. If we had identified Work Center E as our constraint, what would happen? Well, while the queues either side of E may change, the queues upstream of D would be unaffected. Both scenarios will quickly confirm that we had misidentified the location of the constraint and need to switch our focus to work on D instead. There is very little downside to either of these situations, provided we remain alert to how the situation in the plant changes as we implement our improvements and move our focus to D as it becomes apparent that this is our real constraint. The only damage we are likely to have incurred is a short period of lost time, but we will have gained the hugely valuable confirmation of our real constraint's location. Let's now explore what it means to subordinate everything else to the constraint. Step 3 of the 5 focusing steps. Subordinate means that non-constraints must do whatever is necessary to support the exploitation of the constraint. Sometimes this requires non-constraints to behave in a way that many would consider counterintuitive. For example, non-constraints should not produce more than is required to effectively exploit. Just because a non-constraint can produce, doesn't mean that it should. This means that non-constraints will have downtime, as to continue producing would simply result in larger queues in the plant. This is a significant challenge to the culture of many organizations, where the emphasis is put on all resources working as hard as they can. However, when we recognize that only the constraint determines the output of the system, maximizing the output of non-constraints makes no sense, and will only serve to make performance worse. This insight is a profound realization and has far-reaching implications for many areas of our organization. Returning to our thought experiment, we can see that work centers A, B, C, E, and F are now only utilizing the capacity required to support the exploitation of D. This enables us to distinguish between their real level of productive capacity and their protective capacity, the capacity they need to catch up when something has gone wrong, which, as all manufacturing professionals will know, happens fairly regularly. Non-constraints should only go above the level required to exploit, when there has been a stoppage to flow and they need to catch up. Step 4 is to elevate the system's constraint. Steps 1, 2, and 3 are often sufficient to significantly increase capacity, often to the point where improvement is so great that the constraint moves to the market. However, in some circumstances, multiple iterations of exploit and subordinate may not be sufficient to do this. In this case, we need to elevate, which means get more capacity. For example, this may require an investment in an additional machine. This is one of the most powerful and effective aspects of the 5 focusing steps. The framework requires us to focus on improving what we already have, before we invest scarce capital in new equipment or machines. Elevate is therefore step 4. And not step 2. This sequence of activity within the 5 focusing steps has saved many TOC users enormous amounts of money, with Texas Instruments reporting that it had saved them a $715 million investment in a new plant. Applying step 4 to our thought experiment would see us elevate the capacity at D. In this case, we have assumed that the purchase of an identical machine would enable us to double capacity at that part of the process. Doing this means we must now go to step 5 of the 5 focusing steps, which is to go back to step 1, and not allow inertia to become the new constraint. Why? Doubling the capacity at Work Center D changes the situation in the plant entirely. D is no longer the weakest link. We now need to go back to step 1 and reevaluate our assumptions about the system and where the constraint is. The new level of capacity available at Work Center D is higher than the market demand. This means that the new constraint is market demand. All internal work centers have sufficient capacity to keep up, although Work Center B has limited protective capacity, which may be a cause for concern if this part of the process is unstable. The changed situation means we must now reevaluate what it means to exploit and subordinate. This kicks off a new phase in our improvement process, one that focuses on the needs of the customer and making our offer to them more compelling. Let's summarize our learning from this module. The 5 focusing steps is a simple, highly effective, and robust process for analyzing systems and quickly improving their performance. The 5 focusing steps sits at the heart of the TOC body of knowledge. Dr. Goldratt and his collaborators have used this framework to develop specific applications for different environments, such as manufacturing and operations, project management, supply chain, and sales and marketing. The 5 focusing steps makes possible what Dr. Goldratt called a process of ongoing improvement. For him, this was the essence of the theory of constraints. Continuous improvement, by relentless, laser-sharp, focus on improving the system's constraint. This results in an organization continually improving and moving ever closer to its goal. The 5 focusing steps provides the essential process by which we can achieve this in our organization. So let's summarize the steps to conclude the module. Step 1 is to identify the system's constraint, the one thing that holds you back from achieving more of your goal. Step 2 is to exploit the constraint, or squeeze the most from the little that you have. Step 3 is to subordinate everything else to the constraint. Everybody works to exploit the constraint's scarce capacity. Step 4 is to elevate the constraint, or get more of the constraint's capacity. But to only do this when the numerous opportunities to improve from steps 1, 2, and 3 have been exhausted. And step 5 is go back to step 1, and not allow inertia to become the new system's constraint. If you continually strengthen a weakest link, it will not be the weakest for long. You must continually reassess your assumptions and reapply the 5 focusing steps. Remember these 5 steps and you're already on your way to being a TOC pro. And that's it for this module. Great job. See you in the next one.